done. And so I'll tell you about some work that was published recently, mainly about superfluid dark matter and a class of modified gravity theories, where the idea that ties these things together really is using causality as a fundamental constraint on these classes of theories. So just broadly, if I can navigate, yes. I'll try and introduce some motivation for why you should care about these things, first of all, and some of the formalism that I'll talk about for the rest of the hour or so. And then roughly the talk is kind of in two halves. First about superfluid dark matter, and then this class of modified gravity theories. And to give you an idea of where this is going, in the superfluid dark matter topic, using causality as a fundamental constraint, we can see that superfluid dark matter will violate causality in order to do what it's designed to do, which is reproduce galactic phenomenology. So if we try and build a class of theories that doesn't have these pathologies, then rather than thinking of these as dark matter, this will lead us to these modified gravity theories. And then since they're built to satisfy any theoretical constraints we have, it just remains to put some observational constraints on those. So I'll talk about some of that work. So to give you some motivation to think about this, we could spend another whole talk or several talks on the successes of LCDM. And we could also mention that there are known issues on the galactic scale. So cosmological constant with cold dark matter is extremely successful on describing large scale structure and CMB phenomenology. There are these issues on galactic scale or slightly larger. And I won't talk about any of these really. We could devote a whole talk to any of these topics. But the one issue that I want to bring up to motivate the superfluid dark matter is the so-called Tully-Fisher relation. So looking at this plot, this is baryonic mass in say spiral galaxies, disks, versus the asymptotic radial velocity. And a simple collapse model from LCDM predicts the V cube scaling. But looking at this plot, all the data seems to be on the other line, which is V to the 4. So this is apparently a discrepancy between the model and what we observe. So one way to try and resolve this rather radical option is to just say, well, forget about dark matter. We just modify Newtonian gravity in this scale in galaxies, and essentially just insert this factor of 1 over acceleration in the Newtonian force law. And then carrying through some algebra, you can see this will lead to m proportional to v to the 4. So by modifying Newtonian gravity in this way, you would reproduce the observed Tully-Fisher relation. Now, it's very difficult to just modify gravity, right? This is, so maybe you would take this seriously and say, nature is saying, this is the scaling we should have, so we should just modify our laws to reproduce that. So maybe you would say that we should just modify gravity to reproduce this observed scale. But gravity is very difficult to modify because there's a theorem, actually, that GR is the unique causal Lorentz invariant effective theory if you choose to study massless spin 2. So essentially, the only meaningful way you can modify this is to choose to study a different number of degrees of freedom. So you could say massive spin 2, or in particular, we want to think about adding some single scalar degree of freedom, which if it's sufficiently light, then it can mediate some long range force, which could possibly play the role of this new Mondian force. So schematically, what we would like is some relativistic theory that on very large scales can just reproduce cold dark matter. So it just has some canonical Klein-Bording theory. And then on galactic scales has an effective theory with this very particular x kind of kinetic term. So roughly, I'll say this is x to the 3/2. And we can see why this 3/2 scaling is necessary to reproduce the MOND dynamics by looking at the equations of motion and takes a spherical source. Then the force law would have this root m over r squared, which I just showed on the previous slide, leads to the Tully-Fisher relation.
But in this model, so can one cross the point at x equals 0? So x goes 0, then so can one connect the dynamics from minus some x to the positive some x?
Yeah, so it immediately looks very strange that there's a square root in the Lagrangian.
Yeah.
So we have to worry about some basic issues, and I'll get to all of that, preempting a lot of the subject of this talk.
Okay.
Yeah. So, but just to describe what this is in this schematic equation, x is the standard kinetic term, half d phi squared. And in this effective Lagrangian, so x to the 3/2, we see that this can only be an attractive force if alpha, the number that appears in front of the kinetic term, is some positive number. So if we can reproduce some effective theory on galactic scales that has this very particular 3/2 scaling in a kinetic term with a positive coefficient, then by putting in some direct coupling to baryonic matter, so what I'm describing is this sigma b is just some Lorentz scalar that describes baryonic matter. By putting in some direct coupling, then this will lead to the observed Tully-Fisher relation. So this is what we would like to try and have. And of course, we can wonder whether such things are well defined, and we'll get to that as well. So these things are all kind of what we would call k-essence theories. So just broadly speaking, what I mean by k-essence theory is the some scalar theory that can be, is Lagrangian, can be a function of the usual kinetic term, half d phi squared, and perhaps also explicitly a function of the field itself. And we can vary this action in general and find some very nonlinear equations of motion. And so this is not even the most general kind of scalar field embedded in gravity that you can write down. This is a special case of the Horndeski theories, but this is general enough to suffice for us. And so maybe the trivial example of a k-essence theory is if f just equals x. So this is just the canonical theory, which we should hope would be well behaved. And as a somewhat less trivial example, there's this so-called DVI theory, which has been studied as an alternative model of inflation. And I'm not going to talk about that at all, but the reason I bring this up is that it has a known UV completion in string theory. And really, that's the motivation for studying these DVI theories, is that they are supposed to come from string theory. So that's very nice. We know that this should be a well-behaved theory. So we can use this as kind of a prototype. But if we write down some other strange-looking theories like x to the 3/2 or other things, we would like to develop some criteria to be able to test whether these theories are well behaved without needing to find some explicit UV completion. So those criteria are essentially just coming from causality. So in order for the theory to have some embedding in microphysics, to have some potential UV completion, it must respect causality. So this is the ideas that come from the standard effective field theory. So these two criteria essentially are that there's some consistent, well-defined notion of time evolution, or more mathematically speaking, there's a well-defined Cauchy problem, or essentially if I give you some initial data, the theory should tell you how to evolve that forward in time. Or we can say that the equations of motion are always hyperbolic. Okay, these are all saying the same thing. The second condition of no superluminality, you sometimes find in the literature that people claim that this is not necessary for causality as long as you have hyperbolicity. I think these people might be a little bit confused because what we're really talking about here is not just, do you have some solution which you can evolve forward in time and not run into closed time-like curves or something. We're asking whether the theory can have a UV completion. So if the theory has superluminality, then it definitely has no UV completion. So maybe we can argue about causality in that case, but as soon as we say there's no UV completion, then I think we throw the theory out. So that's our reason for including no superluminality in this list. So based on these, the way that we can come up with some mathematical expressions to actually impose these conditions on any k-essence theory is to think about perturbations on top of some background. So we can allow for some arbitrarily high energy perturbation epsilon on some arbitrary background phi b. And to leading order, the equation of motion for epsilon is just this simple wave equation with the effective metric determined just by the background. So from the point of view of high energy particles, the causal structure is just determined by the background value of phi and f, the value of the background. And since these are just arbitrary, we can write this down for any f, any k-essence theory. So since this effective metric determines all the causal structure, we can derive these conditions after some algebra for the theory to respect causality. So I've just labeled them A, B, and C for convenience. So you can remember A, B, and C need to be positive for causality, or C can also go to 0. And I said A and B are both required for hyperbolicity. It's actually technically true that if you violate A and B at the same time, then you recover hyperbolicity. But if that happens, if A and B are both 0 or negative, A and B are both negative, then the sign of this effective metric has completely flipped. So your effective metric now would have opposite signature from the space-time metric. So the high energy particles, test particles, could go from some region without a background phi, which just has a G with one signature, into a region with a phi background with the opposite signature of the effective metric. So in that case, we would still maintain hyperbolicity, but we wouldn't really have an idea of consistent time evolution. So that's why we really say these are 3 separate conditions necessary for causality. So just to show you how this works for the 2 examples that I brought up earlier, for the canonical theory, it's pretty trivial to just take derivatives of this. So A and B are 1, which is clearly positive, and C equals 0. It's slightly less trivial for the dBi theory. So I've written out the A, B, and C here, and you might wonder whether this factor could ever pass through 0. And the reason why I've declared already that these quantities are all positive is because if you pass to the Hamiltonian, so this is essentially the Lagrangian, remember. So if you pass to the Hamiltonian in terms of canonical variables, you would see that when this passes through 0, the kinetic term in the Hamiltonian is diverging. So for stability, we'd say you have to choose either this quantity to be purely positive or purely negative. So you can choose your phase space to just be where that's purely positive, and then you say in the physical region of phase space, these conditions are always satisfied and you always have causality. And this is what we would expect to find since we know that this dBi theory has a UV completion. So it should be what we did. And now we can write down some general power law in X if we like, or I've included some powers of some energy scale lambda just so that the coefficients here are always dimensionless. And so I won't write down the A, B, and C for this theory, but you can imagine doing that, and this would lead to some conditions on the coefficients Gn in order for these class of theories to be causal. And essentially what we find is just what Arkani Hamid and company find in that famous paper. So in other words, this is the so-called sign theorem, which roughly says that all of the even G's must have the same sign, and all the odd G's, the coefficients, have to have the same sign. So what we find from this approach is consistent with that.
They depend on energy or are they constants?
The G's here are just constants. I factored out, yeah, the energy scale lambda. So the G's are just constants. No. Yeah, but so this is just sort of an example of the kind of theory you could think of, but for our purposes of trying to come up with a theory that can do this, that's not going to do the job. And the reason why coming up with some kind of chaos theory that can cover this three halves effective theory is so difficult is because as
maybe I forgot to hear what is theta.
right, I haven't really explained
Oh.
what all these are. All I said was that sigma is something that describes baryonic matter.
Yeah.
Theta is just the strength of the interaction. It's a coupling constant.
Oh,
And
oh,
theta will turn out to be, it's the phase of the complex scalar. So it turns out to be the goldstone in
But
a symmetry breaking
do you
problem.
think this exit? Do you think this scalar field is a complex scalar field?
Yeah, it will turn out that it has to be a complex scalar, and then theta
Oh,
will be the phase of this complex scalar. Yeah, so I'll say that in just a moment. But just to mention, without trying to give some other examples that don't work, to mention why this is difficult to accomplish is because, as Masato was pointing out earlier, the X to the 3/2 theory is not well behaved. So you would immediately see that that theory is superluminal. And more phenomenologically, what we're trying to do is to introduce a new long-range force. So we can worry about whether this new force will immediately violate, say, solar system tests of modified gravity or things like that, just immediately ruled out by observation. So it turns out that a way to accomplish this is to utilize spontaneous symmetry breaking. So that's where this idea of superfluid dark matter comes from. So the theory is supposed to just look like a standard scalar on very large scales. But then in the regime where this second term starts to become important, which is supposed to take place on galactic scales, the theory can undergo a phase transition. And after the spontaneous symmetry breaking, this theta that's left over is the goldstone. And this theta can have this 3/2 scaling, and then if you put in a direct coupling to baryonic matter, it would mediate this MOND-like interaction. And this is, I think, the first explicit example that was able to do this, but there have been many other theories that people have written down since then that have basically the same characteristics. But for example, you could imagine, so this is like x cubed roughly. You could imagine including the x squared term in here as well, or a whole series of other terms as well. But this is the first example that was able to do this. So just to say a little bit more about this, since I think it's a very nice idea. The idea here is that, so you have some complex scalar, that on very large scales, you have some unbroken symmetry. But then when if you break this up into the radial and angular component and write the effective potential for rho, the amplitude, then you would see that in the regime where this term starts to become important, then the effective potential picks up this other term, which gives it a non just purely quadratic piece. So on very large scales, the effective potential is just quadratic in rho. And then as you go into this regime where this second term of Lagrangian is supposed to become important, then you pick up this other bump in the potential. And so you can have the symmetry breaking where rho just gets stuck with this value. And then writing the effective Lagrangian just in terms of theta, the phase, so integrating rho out, we find something that's like this 3/2 scaling, but it's in terms of what I'm calling y here. So y is just a function of it turns out to be the Goldstone theta is the appropriate kinetic term for this non-relativistic regime. And this is also where the Newtonian gravitational field enters, but this is not going to be very important to this discussion. So for the most part, you can just ignore that and just think of this as the kinetic term for theta appropriate in this regime. So also notice that this coefficient that we get here is manifestly positive. So this produces some attractive force when coupled to the baryons. So this coupling is now what you have to put in by hand, but this 3/2 scaling in the kinetic term is what you get from this fancy construction with spontaneous symmetry breaking. So now we can try and check our conditions for causality in this particular Lagrangian. As I said, there are other examples of superfluid theories in the literature, but for this theory, we can check. So if I write down this A, B, and C, which all need to be positive, we would immediately see that A is some positive number plus some things all raised to even powers. So it's manifestly positive. So that's nice. But now B and C can possibly become negative, right? We can't restrict the value of X however we like. In this theory, there's no argument about stability like in the DBI theories. So X cannot be restricted. So B and C can possibly become negative, which would violate causality. Now, we want to know a little more about in what regime this can occur. We know the theory should be well behaved on very large scales, where it just becomes a standard canonical stable theory. So if we look at the galactic regime, the regime where we recover the MOND dynamics, then in that regime, the kinetic term y is just dominated by the gradients because theta is slowly varying in this regime. But if it's dominated by this term, which is negative, then theta is negative. And in this regime, y is negative. So in this regime, B and C become just proportional to y, which means in this regime, B and C are always negative, which violate the conditions for causality. So now this is just in this particular iteration of superfluid dark matter, this particular Lagrangian. And we can try testing this for all the theories in the literature. Yeah.
So does it also indicate the ghost instability?
Yeah, so this would correspond to some kind of ghost instability. Yeah. So we can play the same game for whatever Lagrangian we like, or which we can do, or we can kind of describe this, encapsulate this in one sort of proof by writing this very general Lagrangian, where now I'm including this function f of z, where z is this dimensionless number, which should look familiar from the previous slide. So on the last slide, the Curie-Berzziani theory was just with f equals 1/2 plus 1/6 z squared. So like I mentioned, we can prove the linear in z term, We can include some power series in Z if we like, or our argument is sufficiently general that we can even include non-analytic functions of Z. It doesn't matter. So essentially playing the same game, computing A, B, and C, and checking in the MOND regime. Our conclusions are essentially the same as for that particular example. We always find that A is positive. And then in order to recover the 3/2 scaling with positive coefficient alpha, you always get B and C negative. And it's particularly in the MOND regime that this occurs. So it's by demanding that your effective theory recovers this behavior, this dynamics, that leads to this acausal behavior. So the most we can say from this is that these kinds of theories, these superfluid dark matter theories, would not have UV completion in the standard sense of Wilsonian effective field theory. And that's as much as we can say. Now, I would say that that means that they're not very interesting to study, that they have no embedding in microphysics, but maybe there can be some way around this.
By using two scalar fields, but the one is a very light scalar field, the other very heavy scalar field. Then, so in this original, the Lagrangian basically is most of the kinetic, the kinetic term is just basically there's no linearity in the kinetic term for both of these scalar. But then if I integrate this heavy scalar, then I can essentially get the same kind of Lagrangian as a K sense. So in some sense, in such a sense, there should be some kind of UV completion, maybe UV completion to yourself. It may be able to cure toxicity.
Yeah, so there are,
maybe I guess that this should be some way.
so there are examples of, so you can try and study some theory that does not start with a U1. So you just have two real scalars. And then, so in those kinds of theories, you can construct it so that you recover this effective theory with 3/2 scaling for one of the scalars, integrating out the other. But this same pathology occurs. It necessarily happens as long as you require that the effective theory has this behavior. So all of those theories would fall under this general framework. And we can test those particular theories.
Whatever
explicitly
UV
as well.
completion is, you get into the same kind of.
Yeah, as long as you demand, as long as you construct the theory so that it has this behavior, then it will not have a UV completion as our conclusion.
Yeah, we can discuss it.
Yeah, I mean, so there can certainly be.
Sure, yeah.
Sorry, was there a question?
Sorry,
Maybe not.
could you please go ahead.
Okay, if there wasn't a question, I'll continue.
Okay.
So there are, as far as I understand, these same people are working on other approaches to this problem and trying to construct theories that don't have these pathologies. So they're very different looking, and actually much more standard looking kinds of theories.
Very good.
And it's mixed like France.
Much better than the Portuguese one.
Not sure if someone's asking a question.
So do you have any question? Robots? Okay.
Okay.
So you do have any question? Okay. Yeah. Please.
Yeah. So I just say that to mention that there could be some possibility of theories that look very different from this, potentially resolving this issue in the same kind of way, but they would have to look very different. If we wanted to build theories that sort of look like this, but don't have this kind of acausal pathology, then they would necessarily not play the role of dark matter, since they don't have this phenomenology. But we can instead think of them as a kind of modified gravity theory if we put in some conformal coupling with the scalar. So that leads us to this kind of class of theories. So trying to build what kind of theory can we write down of this form that satisfies all these causality conditions. So we can try and write down this kind of EBI-like theory, as I'll call it. And for this exponent p, when it has the value of 1/2, then we just have the EBI theory. And if it equals 1, then we just have Klein-Gordon. And like the DBI theory, we have to restrict the phase space of X for stability. And now we can compute the A, B, and C for this class of theories and to see what is required for them to always be positive. And if you stare at these expressions long enough, then you'll see eventually that the condition is that P is between 1 and 1/2. So these examples of Klein-Gordon and DBI are actually the two limits of this class of theory, which is kind of interesting. So now we want to try and study this as some kind of modification of gravity. So we have to decide on some conformal coupling. And so this is the whole action. So we have the standard Einstein-Hilbert term, and then our k-essence kinetic term for the scalar. And then in the matter sector, we conformally couple the scalar, and we have some freedom, of course, to choose this conformal coupling factor F, but a convenient choice is this form. So you can think of theta as being the strength of the coupling to matter. And now we immediately have to worry about solar system constraints and things like that. So the well-known constraint from Cassini probe for light bending tests is that the conformal coupling strength theta should be like 3 orders of magnitude below 1 over Planck. So with that as a constraint already, it seems like the scalar should remain light so it can mediate some long-range force. But if we think about the strength of that force, then it seems like it's always extremely small compared to usual force of gravity. So putting in our scalar in this way will just give us some inconsequential interaction that we'll never see. So now it's at this stage that people would usually introduce some kind of screening mechanism. So you put in some kind of non-trivial dynamics that allows you to crank up beta, make this field strength larger while evading the solar system constraints. But in this class of theories, we actually don't need to add anything like that. So it ends up being a kind of anti-screening, is what some people would call this, where we can think of two regimes of the theory. So where X is always less than mu, right? This is what was required for stability. But the absolute value of X could be much greater than mu, so X is large and negative. Then we would enter this very nonlinear regime. And we can think about the strength of the scalar field across various scales. And what we find in general is this relation where if P were equal to 1, so the canonical scalar, then P is equal to 0. So you just have this, which is what I showed on the previous slide, leads to the scalar force being negligible compared to usual gravity. But putting in some other exponent, so putting in some other value of P, leads to some other value Q here, then the force can potentially become large, or it can potentially go faster than the usual gravitational force, as long as this scale, this physical distance r star is large, which is environmentally dependent. So you notice it depends on the mass of the source term, the mass of the thing that the scalar is coupled to. So on laboratory tests of modified gravity, where in the Etbosch experiment, where they have some kind of torsion or some parallel plate experiment, the masses are on the order of kilograms, right? So this R star is extremely small, and we would never see this. But on the other hand, if M is very large, say if you use solar masses, then this transition regime can be astrophysically large. So say look at neutron stars instead of some laboratory weights, then this force can become even larger than usual gravity, while still satisfying the usual solar system constraints on this conformally coupled scalar field theories. So now we can go and look at various neutron star observations to try and build some other constraints on this class of theories. So one thing we can look at is binary neutron star systems. So we want to take some particular value of T. So we can choose T equals 5/6 is very convenient. This gives Q equals 1. So in the orbit equation, the strength of the new force, we call B here, enters roughly the same way that the usual conserved angular momentum does. So we can solve this system relatively easily compared to other values of P. And so essentially how this affects the system is it changes the amount of power radiated into gravitational waves, changes the decay of this orbit. And what is actually measured is the rate of change of the period of the system. So we can say, well, as long as this isn't changed by more than however precise we can actually measure it, then that gives us a bound on the strength of this new force. And notice that this is 10 to the minus 4 compared to 10 to the minus 5. So it's maybe not too useful of a constraint. We can also look at precession, which is kind of interesting that in these theories, it comes in as a leading order effect from the new scalar, while just in GR, without this other degree of freedom, precession is purely a relativistic effect. So we already can have some precession just before even GR. Now, differently from comparing orbital motion, this could, since this is a effect that is only comes down on the next to leading order in GR, this should immediately give us some huge effect that we would see. So this would give us some huge bound on the conformal coupling scale beta. Or we can use this to put some bound on relating beta and the energy scale mu in our theory. So essentially this for a particular system, so for say Holz-Taylor has a certain semi-major nexus. For a particular system, this gives us a bound on the energy scale in terms of the conformal coupling, which we could say satisfies the solar system constraint. And then this gives us some bound on the energy scale on the cutoff of the theory. And we can do this for various binary systems that we're familiar with. They're like the orbit of Mercury or the moon and the Earth, but for some other pulsar binary systems. It turns out the tightest constraint looking at this comes from Holz-Taylor, which is maybe not surprising since this system has been observed for so long and have such good data on it. Another thing that we could potentially think about is whether these binaries can radiate into the scalar mode. So the change to the power that I mentioned before is just the power radiated into the spin 2 mode, but it's still affected by the conformal coupled scalar. But we could also have power radiated directly into the scalar mode. Now it turns out that this is massively suppressed compared to gravitational radiation, so we don't need to worry about it too much. And mostly we think that it should just be irrelevant, but there could potentially be some cases where it's interesting.
So Q is always positive for this range of P. When people debate with half of one, then the Q is always positive.
So this P is the power,
Yeah.
and this is the exponent.
But in the case of P between half and one, then the Q is always positive.
Yes, Q is always positive. So as P is smaller, Q becomes larger. So Q can go from any positive number to infinity as P is between one and 1/2. So yeah, as we make P smaller, we are essentially increasing the strength of the new force and making Q larger. So the strongest constraint we found actually comes from thinking about equilibrium of a single neutron star. And that's okay. So essentially just carrying out the usual calculation for hydrostatic equilibrium, we get some kind of modified TOV equation where we now can think of some effective pressure and density, which are determined by the ksint scalar. So if we put in some very simple kind of equation of state, so just put in the simplest approximation for the equation of state of a neutron star, just to 3 fermions, then we can numerically solve this and get some determine basically the mass and radius of allowed neutron stars in this modified theory. And just to show you all these constraints together, the blue line here, which doesn't depend on the energy scale, is just the usual solar system constraint on the conformal coupling beta. So to be about 3 orders of magnitude times 1/m². So this is basically the one model independent constraint we have. And now thinking about these other constraints that I mentioned, the effect of precession and rate of change of the power, basically the rate of change of the period from this new scalar, are up here. So these are relatively weakly dependent on the choice of P, so the particular choice of theory. But on the other hand, if we go into smaller scales, so even denser regime, which is inside the neutron stars, then changing the strength of the force a bit by changing P drastically changes the bound. So these green lines, the bound from the neutron star equilibrium changes quite a bit depending on the choice of P. So we have several examples here. Basically, as you make smaller, you get a stronger bound because you're increasing the strength of the force. So you can have basically slightly larger, heavier neutron stars. So, all right, just to flash some conclusions of what I talked about. And if anyone has any questions, I'd be happy to talk about that. Thank you.
Thank you very much. Do you have any question?
I can see it seems to be sort of halfway towards the end of the talk, you sort of put gears in it, right? Instead of trying to write down something that gives you the MOND scale, then you focus more on causality. So I can see that it's interesting to study those theories, and right, but isn't it kind of giving up on the original aim? Like is there anything left on the table to actually solve the original aim?
Yeah, you're right that these formulations for trying to solve this issue and recover the dynamics that will lead to this Tully-Fisher relation, we think are in this direction we are giving up on, because we don't see that there's any way to embed that into physics. So don't see any way of doing that from this direction.
Is there another class of modified gravity that does satisfy those conditions that you originally wanted?
That reproduces those dynamics?
Yeah.
As far as we know, there's not, because any theory that is constructed in order to give you those dynamics would fail these conditions, and so not have any degree completion. Now, from what I've seen very recently, these people that came up with this idea of Bayesian theory have studied much more conventional looking theories. And there may be some way to have the same spirit of the idea. But any theory that leads to that effective theory is necessarily pathological.
Well, are there any other question? If not, then let's
Thank you.
speak again.
If you enjoyed the video, like and subscribe.